My name is Dr. Shobhu Sachisyan. I am the Dean Research and Development of JIS College of Engineering. But herein I am here to talk about my physics courses. Okay, I am basically a physics teacher. I do take physics in the classes in the BTech courses, first and second year. So now here I am talking about my second year courses, which is called Physics 2 courses. Now, second year course in Physics 2 is separate for separate branches. For computer science and IT, bouquet is something. For mechanical, civil, it is different. For electrical, electronics, all are different. Obviously, they are learning in a different semester. Now, it is stream specific. It is as per the requirement of your own subject. Okay. Say in the computer science and IT syllabus, we have added the latest computation like quantum computation. Like the applications of latest materials called nanomaterials, how the storage and display devices works. These things are not so much connected with the mechanical and civil engineering, who are also learning physics 2 in this course. So we have kept courses like the ultrasonics, okay, which is applied in mechanical and civil. The concept of building acoustics for civil, which is not needed for you. So basically, we have made it stream specific. We made a thorough analysis of the requirement of your course from your department, from your alumni, from the existing student. We made a survey. Based on that, we have added the topics. So the idea is that it is tailor-made for you. It is made for you only. Okay, what is needed? Okay, for you. You know, all these things you are doing because you, as a computer science and engineering students or information technology students, when you will be passing out, as per because our college is NBA accredited. Okay, some of the courses. So as per the requirement of NBA, you are in an outcome-based system. As NBA guidelines suggests, you should be coming out with 12 attributes, which are called program outcomes. Okay. So now those program outcomes you attend to variety of courses. You'll be in every semester you have got 5 papers. So at the end of each semester, you'll be passing actually coming across almost 35 to 40 theoretical papers, depending on the course. So there are 2 physics courses. Now these courses are there to attend some of the program outcomes. So our course have got some course objective and obviously some course outcome. Now the course objective of this Physics 2 course for CSE and IT student is to introduce topics. Okay, is to apply quantum mechanics for learning the latest of computation called quantum computation. Learn quantum logic gates. Is to, as a student, you comprehend about the hardware sectors of your devices. Okay, the storage, display part, and also the latest storage devices. The entire electronics is moving very fast, and that is because of the revolution in semiconductors and now the nano devices. Okay, so an introduction to that. So that will be another objective of this course. And also this entire communication system, okay, it's based on the electromagnetic theory. Okay, so we'll also provide you some glimpses of electromagnetic theory, because later on you have got courses on the analog communication and digital communication. Okay. Now the major course outcome of this Physics 2 course for CSE and IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design and for the storage material, that is the ideas of nanomaterials. Okay. Now the major course outcome of this Physics 2 course for CSE and IT student is that after undergoing this course, you will be able to explain the electromagnetic theory with your basic knowledge of electrostatics, magnetostatics and electromagnetic theory. You will be able to explain the most modern computing devices using the latest idea of quantum mechanics and quantum mechanics principle. You will be able to explain the operation of the most modern storage devices, how it evolved from the magnetic storage to semiconductor devices. You will be able to judge the requirement of the latest material for the purpose of computing, for the circuit design and for the storage material, that is the ideas of nanomaterials. Okay, so let us, and this is closely connected with your own program, so you can get that in the course outcome, program outcome mapping also. Okay, thank you.
Hello, very good morning. Welcome to day 4 of my quantum mechanics classes. It has been a fascinating journey so far to continue with you in this fourth class. I could say you have been so responsive, you have been so wonderful over the past 3 days. It's my proud privilege that I could offer this course to all of you. Just to remind you that day 1 of the class was mere initialization of the topics which are kept in this second year courses of physics 2 ideas. And this day 3, which is yesterday, okay, the day 4, day 3 was details of whatever we have to do. The concepts of two very important concepts: wave nature of matter, description of the wave nature of matter, concept of the real problem, all those very important issues we discussed. So today we will continue, keep on discussing that. Okay, we have to continue that journey with wave function. And I can assure you, whatever I will be discussing now, okay, in the next 45 minutes or so, it is going to be purely mathematical. Okay, and it has to be because what we did, we had slowly from the direct measurements that we do in classical physics to a mathematical regime, because we are using a function, mathematical function to represent the wave nature of the matter. Now, just to remind you the way how everything has gone, okay, how everything has developed. Just to remind you that story, that in a quantum mechanics course, we our intention is very specific in a quantum mechanics course. I often tell you, and actually I promise I will tell you every day. I'll tell you every day this very little issue. That there are four possibilities that we learn physical science or the physics of matter for that physics of any object for that matter. Primarily, the first thing that we learn in everybody of us learn in school level courses is the physics of matter. Okay, the material nature of the matter, the particle matter, and another idea is that the physics of waves. Okay, the concept of reflection, refraction, the concept of two waves superposing, all these are falling into the periphery of wave property of the wave. Another prospect is that again wave property of wave you studied. Okay, you have attended these ideas of reflection, refraction. In general, we call it scattering, and superposition, experiment, interference in some of the classes. In my class, you learned about the particle nature of the wave, the photonic concept. So material nature of matter, wave nature of wave, particle nature of the wave, everything you know. So what we do in our class, we go for the fourth perspective, which is the proposal of the Broglie, that a matter can show the wavy nature, which is the proof of division of JAMA. And that is the bottom line of our course. In a quantum mechanics course, we'll focus on that issue because that is something uncanny, that is something new, that is something you do not know, that is something we focus upon in a quantum mechanics class. Okay, that is the wavy nature of the matter. And this wavy nature of the matter, these are wonderful pictures, as you could see. And these matter we talk about, obviously small tiny electron orbiting around the nucleus, maybe. You already know these ideas. Okay, the S wave of electron, P waves of electron. These are all talking about the wave aspects of the matter. A lot of time in telling, okay, fine, electron is a wave. It's a wave of what? Who makes the wave? What is the making the wave? Answers to the, it's a wave of chances. It's a wave of probabilities. Because I cannot, it's a highly mathematical concept. This is not like light and sound, not like the variable variation of some physical entities like electric field, magnetic field, or displacement. It is a variation of an object. It's a variation of probability of finding an object. Those pictures are old pictures I've already discussed. Okay, so the quantum mechanical wave we talk about, the wave nature of the matter is not that matter is becoming a wave. The chance of finding the matter is varying at a given point. That variation makes the wave. And this thing also, that these are some of the old pictures that you already know. Just to remind you the way how we have been taking up the whole situation. If any matter moves, okay, the chance of finding the matter is varying. Okay, so the chances are varying means they makes a wave. That is the wave we are talking about. But this can be plus. The waving parameter can be both plus minus. Chance cannot be minus. So we describe the prescription, we followed the prescription of mathematicians. Mathematicians told us, okay, just define that parameter with any function called a function. That is a function of psi. So it's just a function of psi. So we call that as a function psi. Okay, and total probability of finding the particle is obviously 1. Okay, and total probability of finding the particle is obviously 1. Okay, so therefore what we have been trying to tell from the last day onwards, actually, the how in a problem, okay, suppose electrons are moving around, I have to find out its wave function. Okay, the chance of finding, I need to know psi mod psi squared to know where electron is, the probable position of the electron, but I need to know psi first. So who will be giving me psi? So what I told you, let us be more mathematical. Psi is a function of mathematics. You apply common sense of mathematics. What mathematics tells you? How do you get functions? You get functions by solving differential equation. So you solve a differential equation to get the function psi. Now who will give me, okay, that psi is a function. You have to solve the differential equation proposed by Schrodinger. 1926 is a very pure year. Okay, it's an important year when Edwin Schrodinger proposed the equation of motion for a particle in quantum mechanics. Or, in other words, as I told you yesterday, if you're living with classical physics, your equation is the Newtonian idea. If you're living with quantum ideas, your equation is a Schrodinger idea. That is going to give you the wave function psi. And this has been, okay, some of the ideas that you already have. Okay, that these are the classical concepts. These are the classical areas. Classical mechanics ideas, mechanics of large object, as you can see with the examples. Okay, that we describe with Newtonian concept. This is Newton. You just meet him again. Okay. Okay, how Newton, what Newton is doing. Okay, these are all the various examples of classical physics. All of them I can describe with Newtonian idea. And Newtonian equation is a second order first degree differential equation. So this is my working equation of classical physics. But on the contrary, if I have to live in quantum mechanics where the physics is totally different, matter, I have to use a function psi to represent the matter. Psi is just a function. Then my working equation is the Schrodinger equation. You can see the equation there, and the meaning of every term I told you. H cut means Planck constant by 2 pi. V means potential energy. I means root over minus 1. And the mean how V influences your problem, that I told you only in the previous class. From problem to problem, V is going to vary. If V is basically in a problem, if no force acts on the body, then my V will be equal to, look at the elephant, it's beautiful. Just see the elephant, okay? This, just to remind you, this very interesting issue of how potential energy depends on the, potential energy is the product of force into the at the distance. Just F is equal to ma square V square. It is a case of free body or free particle, potential energy time will become 0. Your solution of Schrodinger equation will be very easy, but the realistic problems are like that. Just like this elephant is under gravitational force. Now, there, if I have to solve, if elephant was a quantum mechanical object, then I have to use that expression of V in the Schrodinger equation. In general, the example I have given in the last lecture was the electrons under Coulombic attraction. Okay, so there Coulomb forces are non-zero. So in a problem, you have to put the V and solve the problem. So V is going to influence your problem. If there is no force, V will be zero. Some force is there, V will be non-zero. But ultimately, problem to problem, V will vary, and you actually have to solve the equation. Okay, and this is also a second order first degree equation. We had a lot of discussion last class that classical mechanics working equation, Newtonian equation is also second order first degree differential equation, and the quantum mechanics working equation, Schrodinger equation is also second order first degree differential equation. Now my job is to solve this equation. Question is that how do I solve it? Okay. Problem is that if you don't, if you can't solve the equation, your class is ended today. Okay. And because you see, look at the equation, it's very peculiar. It says equation, it's a second order first degree non-zero. So it's so what I have to do, I have to do I have to do something. I have to learn a bit of more mathematics so that I can actually solve the problem equation in a real problem and get function psi. And after psi doing psi, we can do many more things that I can assure you. Okay, we'll know it. We'll get to know all those information very soon. But the question is that how do I solve it? So what I do, as I was mentioning at the beginning of this video lecture also, that so we'll be doing I'll be teaching about a little technique of solving differential equation, partial differential equation, which is popularly known as the separation of variables. Okay, we'll adapt the technique to convert this equation in beautiful form. Okay, I'll convert this equation of Schrodinger into a very simple form. Okay, and that form is easily solvable form. Okay, in a problem, I'll be okay. It's very easy to solve. Okay, it's very easy to solve. Okay, anybody can solve this equation. Okay, let me do it. Okay, so let us be more mathematical in the next few seconds. Not few seconds, actually, next few minutes. It will be all pure mathematics. Okay, let us do it. Okay, wait for a few minutes. So I hope you can see this. This is the Schrodinger equation. I have to convert this equation into a simpler form. Convert into a simpler form. Okay, I will be converting this into a simpler form. So what is the prescription? Use separation of variable. Use separation of variable. This is a popular technique of mathematics for solving differential equations. Okay, so we will use separation of variable. This is a very popular technique of mathematics to solve differential equation. So now, what to do? What we have to do first? First, let us take a trial solution. Let us take a trial solution. Okay, let us take a trial solution. Now, how the trial solution would look like? Let this be the trial solution. This is my trial solution. Let psi xt be like this much. A exponential ikx minus omega t. Now let this be my trial solution. Now this is nothing new. Okay, this is very similar to something what you do in the normal mathematics, other courses also. Suppose I've got let's just try to look at this type of differential equation. If I've got a differential equation like this, suppose this is my working differential equation. For this type of differential equation, say d2f dx2 plus fx equal to 0. Now, how do you solve this type of equation? You take a trial solution like this much, like fx equal to a to the power mx. So we adapt this type of function as a trial solution. So I'm doing only that much. I'm looking at choosing an e to the power function as a trial solution. But you may ask me, why are you choosing this I here? Why I have chosen? Now this I will take care of the wavy part of the solution, because I know my function psi is a wavy solution. It is going to represent the probability wave of an electron, okay, the wave nature of the matter. So to take care of the wavy part, I have kept I there because of the common sense. Why? Because e to the power of I something, say e to the power ix, it is like only to the power ix. It is like how much cos x plus I sin x. So you realize that this type of quantity to the power of I something is a OV solution, is a periodic solution. Okay. So this is a wavy solution. To give a wavy touch into my discussion, I consider e to the power I kx minus omega t as my trial solution. Okay. Now let us progress in our direction a bit more. So what I have to do, I have to use this much. Okay. This is the Schrodinger equation. This is the Schrodinger equation. I hope you can see it clearly. So this is my trial solution. So what is the trial solution? Trial solution is this one. This is my trial solution. Psi xt is equal to a exponential or e to the power I kx minus omega t. So now what shall I do in the next line? I consider, you see, psi xt I can write down in this way: a1 e to the power I kx into a2 e to the power minus I omega t. Now you can realize the idea is this a1 and a2, they will together make the constant a, and e to the powers are will in multiplication means they will be added in power. Okay, and that is happening here. Now what it does, this gives you something new. It tells you the quantity here, this a1 e to the power I kx, this quantity is something which is a function of x. I call it phi 1x. And the other quantity is a function of t only. I call it phi 2t. So what I am doing, I have got a two variable function psi. I am writing down that as a product of two separate functions. And that is the beauty of separation of variables. Okay, I have separated psi into two parts. Okay. One part is a x dependent part and the other part is a t dependent part, and that is the beauty of separation of variable. I hope you realize it. It's not difficult at all. So what I have to do now, I have to replace all the psi's in the Schrodinger equation, this psi in the Schrodinger equation with the help of these phi's. Now all the psi's in the Schrodinger equation, that is, will be replaced with the phi's. So first person who is going to sacrifice is obviously the d2 psi, del 2 psi, del x2. Now let us do it. Now if you have to replace del 2 psi, del x2, it's a common sense of mathematics. So what I have to do? I have to first get del psi del x. So let me get it for you. Del psi del x is like this much. Okay, you see this is your del psi del x. Del psi del x. So what is del psi del x? Del psi del x is this much. If your derivative partially with respect to x, phi 2 will be constant and it will be d phi 1 dx. You see, this is now exact derivative because phi 1 is a function of one variable and this was partial because psi was a function of two variables. So from here on you can write down obviously the value of the del 2 psi del x2. So now you have to do a double derivative of this. So what would be the value of del 2 psi del x2? Let me write down here in the next line. Del 2 psi del x2 would be this much. Del 2 psi del x2 would be this much. Phi 2 will be again constant. d2 phi 1 dx2. So I have got it. So suppose this is equation 1. So this quantity would be replaced by equation 1. And my next job is to replace the size. Now you can replace the size with the help of this equation. You may call this as equation 2. So you replace this with the help of equation 2. And your next job is to replace the del psi del t. If I calculate del psi del t, then what would happen? You see, you are differentiating with respect to time. So only this phi 2 will be differentiated. So phi 1 will be constant. It will be d phi 2 dt. So this is the, I call this equation 3. So this quantity will be replaced by equation 3. So my next job is to replace all the size with phi's. So let us do it. So it will be like this much. Again, this is Schrodinger equation. I have to keep on writing it for you, okay? Let me reduce the font a bit, okay, to save the space. I hope it is all right for you. I put it in a blue box now. Okay. I hope you can see it properly. So if you start from this side. So by the trial solution, from the trial solution, you already have this one. This was the trial solution. We already have the expression of del 2 psi del x2 as phi 2 d2 phi 1 dx2 del psi del t as phi 1 d phi 2 dt. So now let us do the replacement of it. So first this will be replaced. So this is minus h cut square by 2m. So it will be phi 2t d2 phi 1 dx2. Next is that Vx will be replaced. So Vx will be unchanged. Obviously, the psi will be replaced. Phi 1x phi 2t, because psi is nothing but, okay. I have replaced psi is nothing but this much. Okay, it's the product of phi 1 phi 2. Okay, and on right hand side, I put a blue equal sign. Okay, I hope you can see it there. Right hand side is I h cut phi 1. Okay, I h cut phi 1. I h cut phi 1. D phi 2 dt. So what shall I do now? Every term, the three terms you can see, red and green in the left and black is on the right. You divide every term with phi 1, phi 2. So if I do the division with phi 1, phi 2, my equation takes a form like this. Sorry, it will be in red. Next, it will be in green. And blue arrow, where is the blue? Blue equal sign, sorry, followed by this. I h cut phi 1 divided by phi 1, phi 2. And there is also d phi 2 dt is there. I hope you can see it carefully. So if you look at the equation, you see there this phi 2's will be gone, and here you'll be left with this much, minus h cut square by 2m 1 by phi 1x d2 phi 1x dx2. Next term is this much. Next term is this. Phi 1, phi 2 will cancel. So 1 equal sign followed by phi 1 will cancel. H cut 1 by phi 2t d phi 2 dt. Now I put it in a box, okay? I put it in a green box. If you look at this equation, to the left-hand side of the equation, there are two terms, okay? One in red, another in green, okay? And on the right-hand side of the equation, I've got one term that is in black. And they are separated by one blue equal sign. Now the question is that, can you see anything like t, the time in the left side of the equation? You can't. The left side of the equation is a pure function of x. It's a pure function of x. It's a function of x only. Similar thing is true for the right hand side. Now right hand side of the equation is a function of t only. It's a pure function of t only. So what is happening? You see, I've got an equation whose one side, the left-hand side of the equation purely depends on x, and the right-hand side of the equation depends on t, and they are equal. Now, I have got something special to talk about this equation because this is a very typical equation. I'll give an example, then you'll realize what is the speciality, where the mathematics is changing. Okay, just to discuss it in more detail, how your mathematics is going to change. Now this is again the Schrodinger equation. Each time I change the page, I have to write it. Can't help you. For safety, I keep it in a box every time. So what I have done so far, from this equation, you have got this equation. Okay, this is the equation. Where is the red? By using separation of variable, this is my form of the equation. One by phi 1x d2 phi 1 dx2 plus vx equal to I got 1 by phi 2t d phi 2 dt. What I am telling, left side of the equation, okay, it is a function of x only. And the right hand side of the equation is a function of t only. And problem is that they are equal. Now this is a typical equation of mathematics. I give an example, then you will realize. The idea is that suppose I have got an equation. Suppose, for example, I have got an equation like this: 4x equal to 5t. Here also, left hand side depends on x, right hand side depends on t. Very similar situation. Question is that what is the condition of existence of this equal sign? What is the condition of existence of equal sign? When this equal sign will exist? Answer is that is this much. Suppose this, I choose the x value and t values. Realization is that you can realize if you make this, they both sides will be equal. Suppose I choose t is equal to 4, then I have to choose x equal to 5, 20. Suppose I choose t is equal to x equal to 1 by 4, then I have to choose t is equal to 1 by 5. I choose x0, then I have to choose t0. I choose t8, I have to choose x as 10. So what I am trying to tell you that this equal sign can exist if this table is satisfied. That means what is the speciality of this table? Okay, it is satisfied. What is the speciality of this table? It tells me that if I make t as 4, then I have to make x as 5. Then and then both sides should be equal. If I make t as 1 by 4, then I have to make t as x as 1 by 5. Sorry. If I make t x as 1 by 4, I have to make t as 1 by 5. Then and only then both sides should be equal. So this is just a typical example. If I've got an equation whose one side depends on a variable x, the other side depends on a variable t, you see the equal sign can exist, but under one condition. Condition is that if I choose one of the variables, say t as 4, I have to make x as 5. If I choose one of the variables, say t as 8, I have to make x as 10. Then both sides 40. If I choose one of the variable as 1 by 4, then I have to make the other variable as 1 by 5. If I make one of them 0, I have to make other one also 0. So what I am doing, I am making x and t dependent on each other. They are dependent variable. If they depend on each other, then and only then this equal sign can exist. If they are dependent on each other. That means depending on the value of x, t has to change. If I make x as 5, t has to be 4. Then and only then equal, they will be equal. What I am trying to say, suppose you make, say this is my equation, 4x equal to 5t. Suppose he makes x equal to 5 and t is telling, no, I will become 2. Who will be under danger? This equal sign will be under danger. So if x is 5, t has to be equal to 4. Then and only then they should be equal. Then and only then they should be equal. Okay, then and only then this thing should be equal. Okay. Otherwise, the equal sign cannot exist. So, if depending on the value of one of the variables x, t has to vary. Or depending on the value of t, x has to vary. So, you have to make this x and t dependent on each other. Then and only then this equal sign will exist. So, here also, in this equation of Schrodinger also, we anticipate this equal sign will exist. Here also, one side depends on x, the other side depends on t, very similar to 4x equal to 5 case. And what this example is telling me, the equal sign can exist if both the variables depends on each other. If I make x 5, t has to be 4, depending on its value. If I make x 1 by 4, t has to be 1 by 5. So they have to depend on each other. Then and only then they should be equal. The equal sign will exist. So here also we expect one of the variable is already x, the other one is already t. So these equal sign will be existing if x and t are dependent on each other. Now the question is that, do they depend on each other? What is the meaning of x in my problem? In our problem, x means position and t means time. And you know x and t are two different coordinates. Time is the fourth coordinate. And time does not bother whether x is, suppose I'm sitting here for last 45 minutes. But time is changing, but my position is remaining unchanged. So time does not bother whether position is changing or not. It's a separate coordinate. So in our problem, x means position and t means time, and they do not depend on each other. If that is the story, if I now match up this with this concept, 4 is equal to 5t type of idea, then in my case, x and t are not dependent on each other. X and t are independent variables. They do not depend on each other. Okay. If they do not depend on each other, so this whatever I have discussion made just now, that tells me they should not be equal. If they do not depend on each other, then they can't be equal. But mathematical fallacy is that you see they are already equal because I have started from an equation. And I hope you realize me. Idea is that I've got an equation whose one side depends on x, the other side depends on t. So purely mathematically, if I take this type of example like 4x equal to 5t as I've given you, this tells me these equal sign can exist. They can be equal if depending on the value of one of the variable, other one changes. So they become dependent on each other. But my case, here x and t means position and time, they do not depend on each other. So that means they should not be equal. The equal sign cannot exist. But problem is that they are already equal because I have started with the initial equation. Question is that then how is it possible? That is a mathematical fallacy. We are in a mathematical trouble now. Basic mathematics tells me for the existence of the equal sign, the x and t has to be dependent. But in my problem, they are not dependent. They are space and time. They cannot depend on each other. But even if they are independent of each other, the equation, it's an equation, they're already equal. How is it possible? Answer is that it is possible in only one occasion. Now that occasion is this much. That occasion is this much. Okay, let's note it down. That is this case. Again, my first job is to write down the Schrodinger equation. Schrodinger everywhere. I'm trying to adjust the font every time. Okay. So the idea is that this is the for converted form. After all those, the idea I have taken psi as a product of phi's. This is my formula. Now this is under danger. Okay, so my just last night discussion tells me they this can be these equal sign can exist if x and t depend on each other, but in this case x and t means x means space and t means time. They are independent variable. Then the question is that how it can exist. Oh, so therefore, now this is possible in only one case, as I was mentioning. In only one case it is possible. Now that case is this much. This is the case. Suppose I've got an equation like this much. D to dx2 5x square equal to d dt of 10t. You see, I've got an equation whose one side depends on x and other side depends on t. Now you tell me, suppose x and t are independent of each other, but how they could be equal? If you divide, do the derivative, what do you get? You get 10. And if you do the derivative, what do you get? You get 10. So they are equal. So what is the speciality of the 10? When they are becoming equal? It is a jersey number of Messi or Tendulkar or any other reason. 10 is a number. What is the speciality of 10? What is 10? 10 is a constant. It is a constant quantity. So idea is that the equality can exist if after all the derivative etc. you end up with a pure constant, then and only then they should be equal. If you end up with a pure constant, this is a pure constant. This both sides are giving you a pure constant quantity. This is a pure constant. Both of them are giving you a constant quantity. That means you are not ending up with the x dependent or t dependent term. These terms are not ending up with. So if after derivative etc., if you end up here with a pure constant term, then and only then, even if x and t are independent of each other, they could be equal. So here it is expected from the, because I have got an equation whose one similar case, one side depends on x, other side depends on t, and yet they are, even they are independent of each other, yet they are equal. So it might happen just like this case example I have shown you. Here after all the derivatives, I might have ended up with some constant like 10. And here also from the left right hand side, after all the derivatives, I end up with another constant like that 10. Okay. Same constant on either side, same pure constant on either side. Then and only then they should be equal. So the constants will be like this one. So from left hand side, I get this minus h cut square by 2a 1 by phi 1x d2 phi 1 dx2 plus vx. I will get a constant here. And on the other side, from the other part of the story, I will get this much. I can write it in black. IH cut 1 by phi to t d phi to dt. I will also get a constant. Now let that constant be considered as something like say E. Suppose this constant is something like say E. Why E not ABCD? We'll discuss it later on. So now this is the equation. This is like E is like that 10, and this is the other part of the equation. That is, so both sides are equal to some constant, a same constant E. Now you see what I have done here. This was the original Schrodinger equation. Look at the top. So it was a two variable function. So what I have done now, I have written that as a two separate equation. One equation depends on x only, the other equation depends on t only. And that is the beauty of mathematics. That is the beauty of mathematics, is that it is separated a complex equation, a multivariable function. Here only two variables are there. You can do it for any multivariable function in two parts. One part here depends on x space, the other part depends on t. And now you see they are more easily solvable. For example, this time dependent part, anybody of you can solve it at your age now, because say this is IH cut, I can write down it in this d phi to phi 2 and e dt. So how do you solve this equation? You just take an integration. So how do you solve it? If you integrate, it will be something like IH cut log phi 2, and it will be e dt, and maybe some constant log c maybe present there. Okay, maybe some constant, maybe log c is present there. Okay, so these are easily solvable. Okay, these are easily solvable. This type of solution. So from here, obviously, you can get phi 2 easily. Phi 2 will be how much? Phi 2 will be this much. Okay. Some maybe some constant c e to the power I h cut on either side will go. So it will be minus I e t by h cut. So this will be the solution. Now at your age, anybody of you can solve this. Okay, so it is very easy to solve. Very easy to solve. Anybody of you can solve it. So time part is done. Okay. So it was initially this original equation of Schrodinger equation. This equation was seeming to be very difficult equation to solve. Now beauty of mathematics is that I separated it into parts now, and they are more solvable now. They are much more easily solvable now. Okay. And just like time part, anybody can solve. Anybody of you can solve it. Now let us put some more in focus on the space part, the x-dependent part of the Schrodinger equation. If you look at the x-dependent part of the Schrodinger equation, the x-dependent part is this much. This is the x-dependent part of the Schrodinger equation. Again, I have to write down the Schrodinger equation. It is like this much. Del psi del t, okay. So I have used separation of variable. I have written psi as the product of two functions. Phi's. Now by utilizing this equation, this is one of the equations. This is a constant quantity. So this is my equation in x. And the other equation is the equation in t, which is the other equation. E is a constant quantity. Just now I told you this is easy to solve. You can solve it like this much, c to the power minus I t by h cut. Now look at the x part of the equation. If you look at the space part of the equation, I can do a bit of more manipulation here. I can write down this equation in this way: minus h cut square by 2m d2 phi 1 dx2. Okay, this phi 1 can be taken up. So like this. Is a constant. Okay. So now you compare this equation in blue with the original equation, the left hand side of the original equation, term by term. If you compare both the equation, you will get a very funny thing. You see, I am just comparing. Say minus h cut square by 2m minus h cut square by 2m. Very similar. Double derivative with respect to x, double derivative with respect to x. Function, function, function. Okay. Now next, potential energy term, potential energy term, function, function. If I compare the term by term on the left hand side, compare in left with the starting equation, I get a funny thing. You see, both the equations are very similar. Minus h cut square by 2m, minus h cut square by 2m. Double derivative, function, function, v, function, function, very similar. Excepting only one dissimilarity. What is the dissimilarity? Dissimilarity is that here in the last equation of function only depends on x. It is only x dependent. And in the first equation, it is depending on both space and time. So if I consider first equation as the time, so what is the speciality? First equation depends on time, last equation does not depend on time. So popularly, this last equation is called time independent Schrodinger equation. This is called time independent Schrodinger equation. And obviously the first equation, it is a time independent Schrodinger equation. And the first equation is the time dependent Schrodinger equation. Time dependent Schrodinger equation. It is the time dependent Schrodinger equation. Time dependent Schrodinger equation. Okay, I put it in a green box. This is called time dependent Schrodinger equation. And it's a very popular examination question. Write down time dependent Schrodinger equation and then convert it into time independent Schrodinger equation. 100 times every year in any level of quantum mechanics question, this question has come up. Then you have to follow this step. What are the steps? Write down the equation. Consider psi as a product of two functions. One is x dependent, another is time dependent. Replace all the psi's with phi's. You get an equation. One side depends on x, other side depends on t. Then you continue to so many. You don't have to show any example, just like the way I have did it. I've done it rather. So what you have to show? You have to conclude that if I've got an equation, one side depends on x, the other side depends on t, and if x and t are independent variable, then equal sign can exist if after all the derivatives I end up with a constant like e on both the sides. So the x term will give me some constant e, the time term is also giving me some constant e, and obviously from the x dependent part you get the Schrodinger equation by comparing. So I've got the equation. So the equation of Schrodinger, this was initially it seeming to be a very difficult equation to solve. Now you have got a new version of it. Is the time part and it is almost done as a matter of fact. What I was trying to tell you that uh, in examination, a very common question is that write down time dependent Schrodinger equation and convert into time independent one. That I've done it in this class. Only thing you have to consider these few steps. Write down this is the product of two separate function. Replace all the psi's with phi's. After that, you get an equation. One side depends on x, the other side depends on t. Then you conclude that it is only possible if they're independent variable, if both of them giving you some constant quantity, and from x dependent equation you get the time independent Schrodinger equation. So time part I have already solved. You can realize it is easily solvable. You can do also. So when we be solving actual problem, our main concern will be the v dependent term, because v is going to vary from problem to problem. It is going to vary from problem to problem. So our main concern when we will be solving problems is this with the v part. We'll do that. We'll see that there are some problems in your course. Okay, how it changes from problem to problem. We'll do a magic, okay, when you do it actually. But before that, one open question is that, okay, fine, I'm solving Schrodinger equation. At the end of the day, you're solving a differential equation. But after solving, what you do? Okay, after solving, what you do? What you have to do? Because at the end of the day, now I am telling you that Schrodinger equation, this is the original equation. This is the initial equation, which was depending on both space and time. This is the initial equation which was depending on space and time. Now I have to get the space part and the time part separated. Okay, time part solution done, and space part is this much. This is the space part. Just now I have just shown you, and I am telling that these will vary from problem to problem. So uh, if I1 and the time part was like this much, okay, 1 by phi 2 I h cut d phi 2 dt. So this will give you phi 2 and this is going to give you phi 1, and the product of phi 1 and phi 2 is your psi. Now suppose you have got psi. Now after going psi, what you know, if I take psi square, I should have an idea about the probable position of the object. Probable position of an object. But only knowing position of an object is not called mechanics. Mechanics starts with answering the question position of an object at a given time, but it has got some other facets also. We need to discuss that facets. And is that in a quantum mechanics picture, electron is moving using the psi of electron by psi square of the electron. You can have a probable idea about probability of finding the electron. But only knowing that is not going to give you the full. You cannot full deep into the ideas of quantum world. Okay, you need to know a bit more. Or in other words, if I have to talk about the electronic journey in detail, if I have to consider the how electron moves in a metal, only knowing position is not going to give you the full data. You have to know mechanics means if it is moving, electron should have momentum, electron should have some kinetic energy. How do I get those data? Who knows those data? Because quantum mechanics means key. I have to rely on psi is the only friend of me. From psi square, I can get the idea of probable position of the object. But what else we can do with psi? We need to know that. So what shall I do now? From the next class onwards, we'll switch our discussion a bit, switch in a different direction. Okay, thanks for the time being. Okay. Uh, so these details of mathematical ideas we have penetrated into. We have got the technique of getting psi. We have got the technique of solving Schrodinger equation. It has got two parts now: time-dependent part, independent part. But what we do with psi, that technique we need to learn. Psi is a function. You have to talk with the function. So you need to know a bit of more. Okay, how to deal with psi. And those techniques is called the method of